Exercise 3.2, question 14. We are told that W is a complex nth root of unity with the smallest argument. So I've started the problem off just by thinking about roots of unity. So I said z to the n equals 1, and then you'll note that I've simply written down the roots of unity in the general form. So z equals e raised to the power, in parenthesis, of k2 pi over n, close parenthesis, I. And what I'm now going to do is just list down some of the roots of unity, as shown. Now, we know that W is the root of unity with the smallest argument. Well, a positive argument, I should say. So it can't be 1 because the argument of 1 is 0, of course. So therefore, we can say that W must be e raised to the power of 2 pi over ni, as shown. Now, we're told that n is greater than 4, and if you think about it, that means that the argument of W must be less than 2 pi over 4. So for example, if n was 5, the argument of W would be 2 pi over 5. If n was 6, then the argument of W would be 2 pi over 6. And of course, regardless of what value of n you choose greater than 4, the argument will always be less than 2 pi over 4. We can simplify that down, and that shows us that the argument of W is less than pi over 2, and so the conclusion is that W must lie in the first quadrant, in quadrant 1. Okay, we've now got to show various results involving moduli and arguments of things like W minus 1 and a bit later W plus 1. And really the best way to deal with this problem is by using and thinking of the complex numbers as vectors. So I'm going to start off with a fairly detailed diagram. Now you might want to pause here and have a good look at the diagram to make sure you're happy with everything that I've written here. And importantly, the fact that AB could be considered as the vector journey W minus 1 plus 0i. In other words, you would travel, if you start at the point A and travel back to 0 plus 0i, you would do so by doing minus 1 plus 0i, and then you would add W on, and that would take you up to B. So we can say that we know the distance AB is the same as the modulus of W minus 1, and of course we can find that simply by using the cosine rule. Okay, so if you have a quick look at that, we've got the modulus of W minus 1 squared will be equal to 1 squared plus 1 squared, which of course are just the distances OA, if we call O 0 plus 0i, and to OB, minus 2 times 1 times 1 times by the cosine of 2 pi over n. A little bit of work on that, and we'll end up with this result, that W minus modulus of W minus 1 squared is equal to 2 minus 2 cos 2 pi over n. And if we now think of our trig identities, because we know what we're trying to show here, then what we'll use is the fact that the cosine of 2a is equal to 1 minus 2 sine squared a. If I rearrange that a little, you'll see that 4 sine squared a would therefore be equal to 2 minus 2 cos 2a. And so we can make a direct substitution to say that W minus 1 squared, the modulus of, the modulus of W minus 1 all squared is equal to 4 sine squared of pi over n. We can now take the square root as desired, positive square root, to give us that the modulus of W minus 1 is equal to 2 sine pi over n as required. So far, so good. Again, if you want to pause there and have a good look through the work, do so. Right, the next thing we're interested in is the argument of W minus 1. So again, I'm going to start with the same diagram and fill in some details. And on the diagram, I'm going to fill in what we've just found, and furthermore, I'm going to write down where the argument that we require is. And you can see I've marked it in red, alpha. So that would be the argument of the complex number represented on the diagram as W minus 1. I've also called the other two angles inside beta. We've of course got an isosceles triangle here. And so what we can say is that first of all beta will be equal to pi minus the angle we've got, 2 pi over n divided by 2. a little bit of simplification gives us that beta will equal n pi minus 2 pi all over 2n, and from that we can determine that alpha is equal to pi minus, in parenthesis, n pi minus 2 pi all over 2n. A little bit of simplification by removing the bracket, and so we end up with alpha is equal to pi parenthesis n plus 2 over 2n as desired. So again, so far so good. I'm not sure that the blue squares come on the screen, but never mind. Okay, let's go on. I'm going to use the same diagram again. This is for part C now, and I'm going to extend the diagram, and in fact, as you'll see, I have made a rhombus. So have a look at the diagram. 0 to b is the same as our complex number w, and so w plus 1 will just be 1 unit to the right as shown, and we have this rhombus. Okay, so I'll state that in my solution, and importantly, what does that mean? Well, it means two things actually. It means that CO will bisect that angle, so I can see that the angle AOC will be pi over n, and in fact it also means that the diagonals will intersect each other at right angles, and I'm going to use that fact in a second. Okay, so I've put a couple of other bits of information on the diagram, and what this is going to allow me to do is to find the distance DC, and of course that's the same as the distance OD, so if I know what DC is, I know what OD is, I then know what OC is, which of course is the modulus of W plus 1. So I'm just going to use a little bit of right-angled trigonometry on the on that triangle, what we called it ADC. And so I can say that the cosine of pi over n is equal to the adjacent side, which is CD, over the hypotenuse, which is 1. And so therefore I've got that CD is equal to cos of pi over n, and therefore the modulus of w plus 1 will just be double that distance. Okay, so if I want to write down the complex number for w plus 1, I now know what its magnitude is. It's 2 cos pi over n, and I can see on the diagram what the argument is. It's just pi over n radians. So if I put all that together, you'll get the results as you see in this blue box. Okay, I think that takes us then on to part D. Well, for part D, the first thing we should recognise is that we're dealing with essentially the difference of two squares. And so I've written this down using that identity. Now, the other thing that we should know is that we can therefore write that the modulus of w squared minus 1 would be the same as the modulus of w minus 1 times by the modulus of w plus 1. And I can simply take the moduli of those two complex numbers, which would look like this. And again, I can see that I can use a trig identity that will give me the following result, which of course is correct. What I've used there is the fact that if you multiply two complex numbers together, then what you essentially do is you would multiply their moduli, and of course what you also do is you add together their arguments, and in fact you'll see me do that in this last part now. Okay, so what I'm going to say is that we're interested in the argument of w squared minus 1, and again thinking about that as the difference of two squares, that's the same as saying the argument of w minus 1 times by w plus 1, and if you're finding the argument of the product of two complex numbers, then what of course you do is you add the arguments together. Again, this is a good place to stop, to pause, to test your understanding, to make sure you're happy with why and how we get this result. If you need to look back in your notes, do have a look back, have a think about Euler's form, and really make the connection so you're crystal clear on why I can do what I've done here. That makes the rest of the problem very easy, because all I now need to do is look at my previous work, find out what the arguments were, and add them together, and that gives me this final result you see on the bottom. So in parenthesis n plus 4, close parenthesis times by pi, all divided by 2n. Okay, watch through this a couple of times. If there's any parts that you're not clear about, then of course all you've got to do is come and ask.